Okay, this video is awesome. In it, I'm going to show you how you can see directly electrons. But not only that, but you remember the liquid metal terminator, the metal that had a life of its own. Yeah, that's real. And I'm going to show you how to do it with no special effects whatsoever. And even more, I'm going to show you how to turn metal into gold, something that the alchemists fail to do. And I'm going to do it in about 15 minutes using some of the most abundant compounds in the universe. You see, the most abundant element in the universe is hydrogen. By mass, the universe is about 75% hydrogen. And by number of nuclei, it's about 85% hydrogen. So the compounds of hydrogen are the most common molecules in the universe. So the most common molecule in the universe is H2, hydrogen. Helium really doesn't make any compounds. Now, next down the list, oxygen is the third most common atom in the universe. And the hydride of oxygen is water, the second most common molecule in the universe. It's maybe unsurprising at this point, of course, that 2/3 of the atoms in your body are hydrogen. Carbon's the next most common element in the universe, and the hydride of this is methane, which crops up again and again all over the solar system. Neon and iron really don't form much in the way of hydrides, and next down the list is nitrogen, and the hydride of nitrogen is ammonia. And it's maybe not unsurprising at this point that if you take a look at the outer planets, they basically reflect this. They're mostly hydrogen and helium with a bit of water, methane, and ammonia. So what is ammonia?
Cool, so this is ammonia. Well, this is the tube that comes out of it. It's a gas. So as you get this going, you'll be able to hear the gas going. And, oh, yeah, even now, you get a good whiff of ammonia, and it's kind of like getting hit in the face. It's, yeah, that's how sharp it is. It's really sharp, but relatively short-lived. And then it's more or less the same if it gets in your eyes. It stings like crazy, but it doesn't have for a long period of time. It's a bit weird like that. Anyway, so that's ammonia coming out of there. And as you can see, it's a pretty reasonable gas. So how do you make this into a liquid? Well, there are two principal ways that you can do it. The first is you get it really cold, which you would do with a block of carbon dioxide like that. Or you can pressurize it, which you would do in a cylinder. So there's our block of carbon dioxide, and we need to break some bits off that. You can just about move this stuff with your bare hands, but you get frostbite, really, burns, freezes your fingers really pretty quickly. And it does all sorts of weird stuff. I'll show you in a second. But you can just sort of break up your carbon dioxide like this. We want a few blocks. Yeah. So here I've got a thermometer. It's 22 degrees Celsius at the moment. That's room temperature. That's a block of carbon dioxide. Makes these. That's basically the gas vaporizing, and does all sorts of weird stuff. Right. So that's basically the temperature of the carbon dioxide is -78, but obviously pushing stuff into carbon dioxide is a pain in the ass because this is a solid and doesn't have a very good conductivity. So what I'm going to do is I'm just going to get some ethanol and pour the ethanol onto the dry ice, at which point it does some interesting stuff. So that's now like carbonated ethanol, fizzy ethanol. But the good thing is it should have a temperature of minus plenty. So this is now a liquid that's actually really cold. I only need like -30 to liquefy the ammonia. So this will now easily liquefy ammonia. So here I have my tube with ammonia. If I actually just blow my ammonia into this pot here, absolutely diddly squat happens until I sort of stick it into the liquid, the ethanol dry ice bath. At which point you should find you start to get stuff condensing in there. It does actually condense really quite quickly. And yeah, that's basically liquid ammonia. There are various ways I can demonstrate that this is actually liquid ammonia. Maybe the simplest is I'll just pour it into another little ampule. And just how quickly it boils off, you see. But this is actually still quite cold.
Cool, so that's liquid ammonia. Now, if you get sodium and add it to water, the second most common molecule in the universe, you get a pretty decent explosion. Which is related to the electrons from that sodium going into the water. This was explored at some length on this channel and actually resulted in a publication in a very prestigious science journal. So what happens is the electrons get sucked off the metal into the water, where they have a very short lifetime because the water reacts with them so quickly. Now, when we did this work, we found we had to work with sodium potassium alloy because it was possible to get this really clean metal surface with it, which is again remarkable if you think about it. You take sodium, which is a solid, and potassium, which is a solid, and you mix the two together and you get a beautiful liquid metal. It goes a little something like this.
So what I've got here is some potassium and some sodium. They've both got about the same density, and so the ratio of the volumes basically gives me the ratio in which I'm mixing them in, which is approximately 4 parts potassium to 1 part sodium. You see there's all this oil and crap on here, so I'm just going to wash some of that off. I'm going to chop up the potassium into little bits or smaller bits and put them in a second pot of hexane. So the sodium I'm going to chop up smaller because sodium is actually much harder as a metal. As you can see, it's easy enough to cut. It's sort of like hard butter. Good. That's all our sodium and potassium in there. Now comes the interesting bit, which is when you actually squish these two together. I want to get on the microscope here. There you go, you see? Liquid. You push two solids together and you get liquid metal, no less. Transfer it from one to the other using a syringe. Just one of these incredible things. You get this beautiful metallic liquid in the syringe. Let's see if we can actually. That's actually metallic sodium potassium alloy in the syringe there. There somewhere. Oops. And one single drop of ethanol. Let's see what that does for us. Oh, it's a bit vicious, a bit vigorous. Now, so, and after that, you've got this beautiful metal. You can hardly tell it's metal at all, it's that shiny. Cool, right.
So when sodium potassium alloy reacts with water, you get a pretty decent explosion. Cool, so that's the reaction with water, the second most common molecule in the universe. What about with ammonia, the fourth most common molecule in the universe? Well, something even more remarkable happens. You see, in water, the electrons drift into solution very quickly, but react with the water. But in ammonia, they drift into solution very quickly, but they don't react. They just sit there as solvated electrons. And it's not hard to spot when this happens.
Okay, so there we have some freshly condensed liquid ammonia. There we have some sodium potassium alloy. Now what you think is going to happen when we put our metal, beautiful metal, into the sodium potassium alloy? Instantly it goes blue, like crazy blue. Get that nice and cool. Now if we put another drop in there, let's see if anything interesting else happens. And you can see it starts going metallic. Yeah? Absolutely crazy. It's this beautiful metallic liquid.
Now that blue colour you're looking at is single solvated electrons in solution. And as the concentration gets much higher, you get this weird transition to this sort of metallic liquid, which is actually a really concentrated solution of these solvated electrons in ammonia. Now those solvated electrons are almost unique in the whole of chemistry. You see, what normally keeps the negative electron mostly in one place is a potential well, a sort of electrostatic hole into which the electron falls, and that potential well is caused by a positive charge, specifically a tiny atomic nucleus. That's basically what keeps the electrons there, and that's the case for almost all the electrons in your body. This, on the other hand, is completely different. Here that potential well, the electrostatic box that keeps the electron all in one place, is actually caused by the solvating ammonia molecules. In fact, it's just one of the most remarkable things to sit there and watch when you understand what's going on, is you get some liquid ammonia and you put a bit of electrolyte in there, say lithium chloride or something, and then you pass electricity through the solution. You electrolyze the solution, and the electrons just simply fall off the electrode and go into solution. But maybe one of the most remarkable things here is when the concentration gets really high with these solvated electrons, where the concentration gets so high that they essentially form a band structure, and it goes from being this dark blue solution to one that's more bronze or gold in color. Now imagine another experiment that we're just going to get a tube and we're going to pass an inert gas through it, and we're going to put a single drop of sodium potassium alloy in there. And just for the sense of scale, that's the tip of a hypodermic needle there. And then we're going to dip all of that into our alcohol and carbon dioxide cold bath. And then we're going to add ammonia to that inert gas stream. So what happens is the ammonia starts condensing on the surface, and you get these really cool effects. And it's also helped by the fact that we can actually turn off the flow of ammonia, at which point the ammonia starts evaporating into the inert gas stream. And you just get some of the most beautiful things that I've ever seen in science. I hope you enjoyed that, and if you did, please consider giving this video a thumbs up and subscribing. And if you really like what this channel does and want to support competent, independent media like this, you can support this channel directly through Patreon with the links below.